Today is February 2nd, 2012. I'm Larry Gallagher, and today I am talking with Walter Lewin as part of the MIT 150 Infinite History Project. Walter Lewin was born and raised in the Netherlands. He came to MIT in 1966 as a postdoctoral associate in the Department of Physics and was invited to join the faculty as an assistant professor. Professor Lewin is a highly accomplished astrophysicist and a pioneer in X-ray astronomy. In addition to his groundbreaking scientific work, Lewin taught the 3 physics core classes at MIT for more than 40 years. His lucid and engaging lectures were hugely popular and introduced thousands of students to the beauty of physics. Lewin's lectures are still among the most popular items on MIT's courseware, MIT's OpenCourseware, and iTunes U, and are viewed by about 5,000 people daily from all over the world. Professor Lewin retired from MIT in 2009 and is now a professor of physics emeritus. Welcome, Walter, and thank you for taking the time to talk with us today.
My pleasure, Larry.
Walter, as noted in your introduction, you are an accomplished researcher and a renowned teacher. How did you balance the demands required to become so accomplished in both areas?
That's an excellent question. There were times that I did research, and there were times that I lectured. And when I lectured, my graduate students didn't see much of me, because when I lectured for the freshmen, for 600 people, I put in 85 to 100 hours a week. And my graduate students knew that. But there was so much momentum in my research that I could afford doing that one term, provided I did it only, say, once every 2 years.
Right.
And so
did you do things, you did things in phases then? You'd have a research phase where you'd put most of your energy there, and then a teaching phase.
That's right. I also negotiated most of the time if I would take on a major lecturing responsibility for some 500-600 students, that I would get one term off, which was always granted. So surely during the 6 months or during the 3 months that I would lecture, I would still be involved in the research, but very remote, at a distance. Whereas all the other time I would work 100 hours a week on my research,
Right.
Including summers.
Right. You grew up in the Netherlands during the horrors of World War II.
That's correct.
Would you care to talk about those experiences and how they have shaped the person you are today?
Larry, that cannot be answered in 3 hours.
Uh-huh.
My grandparents were gassed in Auschwitz. Half my family was murdered by the Nazis. I went through the hunger winter in The Hague in 1944 when we ate bark of trees. We ate tulip bulbs, and you get paralyzed when you eat tulip bulbs. There was no electricity. There was no transportation. My father was a Jew, but he went underground, and thank goodness they never found him. The rules, the laws, how they changed because of the Nazis, was like water coming slowly up. In other words, the first thing was that my father could not walk in parks. Well, my father would say, how often do I go to parks? Then my father was no longer allowed to go to restaurants. My father would say, well, how often do I go to restaurants? Then my father was no longer allowed to use public transportation. Then my father would say, well, how often do I use public transportation? Then my father was no longer allowed to walk on the street after 8 o'clock. And my father would say, well, how often do I walk on the street at 8 o'clock? And so very slowly, I've seen this water coming here and high, rising and rising and rising. And I've still nightmares about it.
Mm-hmm.
I occasionally dream that I witness my own execution. I occasionally dream that the Gestapo executes me.
Despite these horrors, I read in your book that you said that after the war, in your words, you had more or less a normal childhood. How did things shift so quickly?
Well, I do not know what quickly means. When the war was ended, I was 9. My father was back home. He survived the war. Of course, we had to digest at that time the fact that we were pretty much sure of, but never 100%, that my grandparents were gassed and that my uncle and my aunt were murdered. But life goes on, and so I say within a year or so, by 1946, my father's business got going again, because obviously as a Jew he was not allowed to have any business. In fact, he wasn't even home. Mm-hmm. So I would say after 1946, my life became again quite normal, and not much different from other people, other than the scars of the war. But everyone had scars in some way. But because of the fact that I was half Jewish and my father's family was Jewish, my scars are probably a little bit more severe, mm-hmm. and are still there today. Mm-hmm. There is not a single day, Larry, not a single day that the World War II is not on my plate. Mm-hmm. I can almost say not a single hour.
When was it that you first realized you had a special love of science?
Oh, it was very late. Yeah, that was maybe the last 1 or 2 years of high school.
Was there an aha? Was there an epiphany? What was it?
So many people have asked me that question. It wasn't from one day to the next. Right. There was a friend of ours at home who sometimes helped me with my homework, believe it or not, with my algebra, with my physics, with my chemistry. He was a chemist himself. And I slowly began to realize that when you come to think of it, it's actually quite easy. Science is there to make difficult things easy. The man on the street thinks the other way around, but it's completely wrong. Right. They think that physics is there to make easy things difficult, because when they think of physics, they think of equations. But I don't think of equations when I think of physics. I think of concepts. And the amazing thing with physics is, and I'm sure that holds for many other scientists, that the most incredibly difficult things can be understood and calculated in seconds. Mm. Whereas without that background, without that mathematical structure, there would be no way. Mm.
When did you first start looking at rainbows, for example, and saying, I wonder how rainbows are formed?
All right, that was during my student years. There is a book written by a very famous professor in the Netherlands, Minnaert. And he wrote a book, in Dutch it's called Natuurkunde van het vrije veld. It is translated in English. I have the English version also in my office, although I really cherish the Dutch version. Mm. But he discusses all kinds of events. Event is not the thing. All kinds of phenomena mm-hmm. that you see in nature, including the waves on canals, what conclusions you can draw from that. And glories, when you fly over clouds and you see beautiful colors. And of course he also discusses rainbows.
And when did you first read that book?
I would think that it was presumably in my freshman year or my sophomore year.
In high school?
No, university.
Oh, university.
Oh, that was university. It was not high school.
Oh, interesting.
So I was already 13, 14 years old.
Right. And how and when did you first develop your love, your passion for teaching?
I think that came very early. It appealed to me somehow. It's, in a way, part of my personality, I think, to teach people. And so when I got my master's degree, and I wanted to continue for my PhD, I was given the option by the government to teach 5 years full-time at a high school, at least 20 contact hours a week. If I did that, then I didn't have to was not going to be drafted in the army, which was in those days 18 months for every Dutch person. It would have been a total disaster for me to get into the army. I would be scrubbing toilets every day, believe me, because I can't stand authority. And so I would clash with them every day. In addition, I had a fellowship from the government, and every year that you would teach physics, because there was a shortage of physics professors, they would reduce your debt by 20%. So after 5 years, no more debt. And then, during those 5 years, I got my PhD. So needless to say, that I worked day and night.
You also write that your parents ran a school out of your house.
Yep.
So that must have influenced you as well.
No, I don't think that had anything to do with my teaching. That was for adults in the evening. I was a teacher there on typewriting and shorthand for a while when I was a student, and I made some money that way. So my father hired me instead of teachers. Right. No, I don't think that was particularly... no, I wouldn't call that the starting point of my desire or my love. Love is a better word than the love for teaching. Right. That really came when I was 5 years in Rotterdam at that school which is called the Lebanon Lyceum. And I still, nowadays, you remember how long this is ago, this started in 1960. I still nowadays sometimes get letters from people who thank me for the way that I have made them see the world in a different way. And at the time then, I was not aware that I was doing that. Now I know that's my goal. Right. My goal now is and has been for the past 40 years at MIT, to make people see the world in a new way, in a way that they never would.
Right.
But I already did that up at Lebanon Lyceum, apparently.
So, and that was with students that were only a few years younger than you were.
That's right. They were only a few years younger. Right. Some became friends later.
Yes. And do they have they followed? They had you in the classroom then, and then they're able to see you on the internet now. Do you hear from them?
I get emails from them.
Yeah.
They see me at internet. Yeah, of course. Okay. And I was recently on Dutch TV, which was viewed by 1.5 million people. And boy, the number of reactions that I got from my old students was enormous. And I gave a lecture in Delft by my university 2 days later after the TV performance. And there were many people from the Lebanon Lyceum. And of course, I didn't recognize them. It was almost half a century ago. Sure. So some people say, don't you recognize me, Professor Lewin? 50 years ago, not a clue. No, you don't even remember names, except a handful that always remained in contact with me. In fact, there's some with whom I still exchange email weekly.
What was that lecture that you gave it?
Oh, the lecture I gave in the Netherlands on October 26, 2011, was about rainbows. Rainbows and blue skies and white clouds. Why are the clouds white and why is the sky blue? And why are rainbows the way they are? And my first question that I always ask is, I ask the class, I ask my audience, I ask the people in Delft, have many of you seen rainbows? And then, they've all seen rainbows. And then my reaction is, no, you've never seen one. You've looked at rainbows, but you've never seen them. Right. Just like art, you've looked at art, but you may never have seen it. And after this lecture on rainbows, it will be the first time in your life that you will actually have seen a rainbow, and it will change your life forever. You know that I get daily at least 5 rainbow pictures from people from all over the world. I don't even know what to do them, and sometimes I don't even look at them. I get too many.
Yes. Right. Let's go back to your years in college. It's for your PhD thesis. You studied radioactive decay at Delft University of Technology. Please tell us about that.
Well, yeah, there was a theory at the time that certain decays form either the product is a gamma ray or the product is an electron, if I try to simplify the matter. And the fraction gamma rays to the fraction of electrons was theoretically predicted. And there were indications that the theory was wrong. And one of the things that I did in a few cases, 4 or 5 I remember, to demonstrate to an enormous degree of accuracy that the theory was correct. So the whole idea with physics is the degree of accuracy is what counts. If someone comes up with a number that is 10% accurate, that is nowhere nearly as interesting as someone who comes up with another number which is 1% accurate. Mm-hmm. And so for me, the great accomplishment was that in order to prove that the experiments which claimed that the theory wasn't working, I had to decrease the uncertainty in my measurements to show them that they were wrong. And I succeeded.
And precision is a very important part of your teaching. You talk a great deal about the importance of precise measurement. You proclaim in your first lecture in MIT Physics 801 Classical Mechanics, quote, "Any measurement that you make without knowledge of its uncertainty is meaningless," close quote.
I said it 3 times during that lecture. Because a number without the uncertainty of the number is totally meaningless. Mm-hmm. Right. What does it mean when I say this table is 76 inches long? Does it mean that it could be 77? Could it be 78? Maybe it's 72. But if someone says, this table is 76 plus or minus 0.2 inches long, now that's a hell of a lot better. And so in my first lecture, I bring something to a test. And they will never forget that. My grandmother told me when you lie down, you're taller than when you stand up. Now, how do you prove that? If I measure a person stand up and having a person lie down, and I measure that distance in inches, that means nothing. I have to know the uncertainty in each measurement. Only then can I make the case. So what do? I have an aluminum rod, which is about 6 feet long. I measure the aluminum rod vertically, and I measure the aluminum rod horizontally. And I show them that I can actually measure the length of that rod to an accuracy of 1 millimeter in both cases. And so even though the 2 numbers are not the same, it never is because there's an uncertainty in everything you do, they were within 1 millimeter the same. So I demonstrated to my class. What I'm going to do with a student now has an accuracy of 1 millimeter. Then I put a student vertically. I measured him. Then I put the student horizontally and I measured him. And the difference was 3/4 of an inch with an uncertainty of 1 millimeter. So I had absolutely, conclusively, beyond the shadow of any doubt, demonstrated that indeed you're taller when you lie down. And now you see how important uncertainty is. Because it's only meaningful, the statement, that you're taller if you can demonstrate that by making your uncertainty that small. So now you see my statements that any measurement that you make without knowledge of uncertainty is meaningless.
And it's so nice to be able to capture some of the passion of your teaching in this interview, as you've just demonstrated. Let's go back and can you talk about how you happened to come to MIT and what enticed you to stay? How did your MIT experience differ from your time at Delft?
Apples and coconuts. The difference between hell and heaven. That's a little bit of an exaggeration. In the Netherlands, in those days, as a graduate student in physics, you were treated in a way that was almost inhuman. There was no way you would get a key to the front door. Oh no. You get a key to the basement. So you had to go in through the basement to make you really feel that you were nothing. I worked with radioactive isotopes. That means I almost always had to work through the night because radioactive isotopes decay. And when they decay, they get fainter and fainter, weaker and weaker. And then ultimately, I have to stop measuring. So I sometimes work 60 hours straight. They demanded that every day before 4 o'clock, I had to submit an application to work that night. They did everything to make my life miserable. There were parking places for 3 professors in front of the building. Yeah, I had a car. I was not supposed to park there. But my own supervisor was a wonderful man. He wasn't like that at all. He wasn't a bureaucrat at all. Only came on Tuesdays. So I said to him, his name was Aldert Wapstra, I said, Aldert, since you're only here on Tuesday, do you mind if I use your parking place during the other days? He said, of course you can use it anytime you want to. So I parked my car there. Over the intercom, Walter Lewin, remove immediately your car. It was terrible. And so I had the feeling that everything was done there to hold you down.
Right. So when you started...
And I was a little bit eccentric and maybe also at times therefore a little bit obnoxious. Mm-hmm. I collided with the system. And here I come to MIT.
And how did MIT come across your radar screen?
Okay. Very good question. My supervisor, Aldert Wapstra, who was a nuclear physicist, was given an offer to become professor in Utrecht. We were in Delft together with Wapstra, to become a professor in Utrecht in a new area, which was space research. The Netherlands had done no space research. You know, you're talking now about 1965, 66. And he asked me whether I would want to become his second man, sort of like vice chairman, vice president, whatever you want to call that, of that institute. And that appealed to me because I did see really the end of the kind of work I was doing as a nuclear physicist. I saw that. It was low energy nuclear physics. It was not the particle physics. And so I said to Aldert, I said, look, it's fine, but you know nothing about space research. I know nothing about space research. So I think I should go for 1 year to the United States and see what they do in space research. And so he wrote a letter to Bruno Rossi, whom he happened to know, and he wrote a letter to John Simpson at Chicago. And they offered me both a postdoctoral position for 1 year. Mm-hmm. I even signed papers with the Netherlands that I would come back after 1 year. And there was even a penalty, a financial penalty, if I decided not to come back. So I came here on January 11, 1966. I know the date so well because we were supposed to go on January 4, but one of my kids got the mumps, and then the airlines won't fly you. And then my doctor said, your second kid is going to get it too, but there is a small window in which you're not contagious. And so we went on January 11, and indeed 3 days later, my other kid got the mumps. So we arrived on January 11. Half a year later, I was offered here a professorship. So I told the Netherlands to go to hell. I stayed here.
So given the restrictiveness of the ways things were at Delft and the relative freedom and openness of MIT, how long into that 6 months did you know you weren't going back?
I knew I had to go back. It was only until a professorship was offered that all of a sudden MIT was willing to change my J visa, which was only good for 1 year, into a green card visa. That's a long process. But once MIT makes the case, right or wrong, I do not know, that they say, because I worked with NASA grant funding, you know, Walter Lewin is indispensable for the country, has special knowledge, is important for NASA. You know, they can make the case. Right. So I knew that I could stay here. But for the first 6 months, I just assumed that I had to go back.
And when were you first struck by how different things were between the two places?
But what do I what?
How were you first struck with how different things were between
Day
the way
one.
MIT does things in a way?
Day one.
What,
Totally different atmosphere.
explain.
I got a key to the whole building. I could open every door in the building. It was building 26. I could literally open the door of everyone's building. What an amazing trust they give you. I could work day and night. I could come in at 3 o'clock in the morning. I didn't have to fill out any forms. I could do anything I wanted. I could work Sundays. I could work Saturdays. It's a whole different world.
And you were
There's one thing, however, I want to stress.
Yes.
I owe the Dutch system a lot. And the best way to express that is that my grandfather on my mother's side could neither read nor write. 2 generations later, I became a full professor at MIT. That was only possible because of the Dutch educational system. Socialism. Without socialism, that would never have happened. I am a Democrat for 105%. I've really seen what socialism can do for people. I've also seen the negative parts later in my life. But I really owe the Dutch in that sense a lot. But boy, did I leave at the right time.
In fact, you state that when you came to MIT, quote, you were exactly at the right place at the right time.
Yeah.
Explain.
Pure luck. Well, okay, by the way, so how did I make the decision between John Simpson, Chicago, and MIT, Bruno Rossi? A lot of my work that I had done for my nuclear physics was with electrons, and I had done a lot of work with X-rays. Now, the problem with electrons is electrons move around in magnetic fields. X-rays don't do that. They go straight through. So I decided if I'm going to do space research and I'm going to measure electrons, I don't have a clue where the hell they were coming from. They may come from this direction, but who knows what they have done on the way to me. Whereas an X-ray, if I can position in the sky where the X-ray comes from, that is line of sight, that's straight. So I decided it's much better to take X-ray astronomy. Mm-hmm. It could not have been a better choice because X-ray astronomy was discovered in 1962. Bruno Rossi had this insight of giving that a try, and it was brilliantly worked out by Riccardo Giacconi, for which he later received the Nobel Prize and deserved, in my book, the Nobel Prize. And I came here in January 66, and their first paper was December 62. So 3 years in between. Mm-hmm. So I came in there when the field was absolutely at its start. And then George Clark invited me to become part of his group. He was very, very generous to me. And so anything that we did in the early days, almost anything was pure gold, because nothing was done. I was the first one to fly balloons at very high altitude in the southern hemisphere. Boom, 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 one discovery after another, because no one has ever done it. So that was an unbelievable stroke of luck, really luck. The right person at the right time, at the right place. 10 years later, I wouldn't have had that impact. Mm-hmm. 10 years earlier, X-ray astronomy did not exist. So yeah, you need sometimes luck in your life.
Well, we're going to talk a little bit about your research, but I just want to ask you one simple question, and not very simple, but why is it that physicists love astronomy so much?
Oh, I think everyone loves astronomy because it's so visual. You see the moon, you see the stars, you see planets occasionally, you see a comet, and occasionally you see meteors in the sky. So everyone, I think, deep in his heart has a feeling for astronomy. And I notice that. I'm on Facebook, and I'm on Facebook not for physics reasons, but for art, because art is one of my real love. Mm-hmm. Physics, I always say physics is my life, but art is my love. And all these artists with whom I work on Facebook, they have an enormous appeal for astronomy somehow. Here's a rover on Mars which runs around, take pictures of pebbles which are this small. I mean, that's an incredible thing. Perhaps physicists a little bit more than the non-physicists, because we have the background, we have the knowledge.
Exactly.
It's incredibly fascinating, astronomy. Astronomy is physics. Let's face it.
Right. Let's talk a little bit about some of your key scientific accomplishments, starting with X-ray ballooning.
Yeah, that's where it started with. When I arrived at MIT, most of the experiments that were done by rockets. They fly the rockets above the Earth's atmosphere because the Earth's atmosphere absorbs X-rays. If you're completely way outside the Earth's atmosphere, completely outside, you have to be more than 80 kilometers up, then the atmosphere has no effect anymore on absorption. But the rockets were only up there for a few minutes. You fly them up and then they go into free fall and they return back to Earth. So they only had a 5-minute view of the sky. And what we didn't know at the time, what we know now, that most of the spectra from X-ray sources have an enormous abundance of low-energy X-rays and almost no high-energy X-rays. So these rockets were only sensitive to low energy because they were only 5 minutes up in the sky. So then it was George Clark in 1964 who flew the first balloon at a very high altitude of about 140,000 feet. There's still a little bit of atmosphere above you, so you cannot see the low energy X-rays, but you can only see the high energy X-rays. So in that sense, the rockets were never in competition with the balloons because the balloons could stay up 10, 20 hours. And they therefore could detect and did detect the high energy X-rays. And so I joined George's group. And so and then he turned the entire group over to me after a few years. And so I was the first to go to the southern hemisphere with those balloons. And so without competing with rocket people, we discovered many X-ray sources which had never been seen by rockets. But not only that, which I consider way more important, often forgotten nowadays, but it's so long ago. In 5 minutes, you look to as many sources in the sky as you can. We had 20, 30 hours. Right. We could look at one source for hours.
And you used to follow...
And we discovered that those sources vary their intensity. We discovered that. If you tell that now to a graduate student, they sort of smile because they know that every source in the sky varies, but they forget that we discovered that. And so not only were we able to measure a part of the spectrum, the high energy part of the X-ray spectrum, which the rockets couldn't, but we even were able to demonstrate that the energy, the power output, varies by enormous factors of 10 over a time scale of maybe half an hour. Imagine that the sun would become 10 times brighter in 10 minutes. Would scare the hell out of you, wouldn't you? Well, X-ray sources do that.
Mm-hmm. How is that data communicated? I know that you used to follow the balloons around in a small plane.
Well, in the early days, we recorded the data on board on film. Later, we would transmit them by radio to Earth. Okay. Yeah, we would fly, the balloon would be at 140,000 feet. And airplanes fly at 30,000 feet, so it's 5 times higher. And we would stay with the balloons as long as, particularly at night, we were in radio contact with the balloon. We could give commands also from the plane. And then when the balloon gets over area where airplane lanes are, then you cannot fly over there. Matter of safety. Then you have to terminate the balloon. You do that on radio command. You separate the balloon from the top of the telescope is attached to a parachute, and you separate the parachute from the balloon, and then it comes down.
Can you talk about your discovery in 1967 of the first rapid X-ray variation?
Yeah, that was Sco X-1. That was the famous October 15. I never forget the date. On October 15, we measured, I think it was in Mildura, Australia, from a balloon flight, that Sco X-1 went up by roughly, if I'm not correct, yeah, I think almost a factor of 4 or 5 times brighter on a time scale of about 10 minutes, and then it decayed away again, roughly on a time scale of 10 minutes. And this was such a totally bizarre thing. You must imagine, how can the sun, on a time scale of 10 minutes, becomes 4 times brighter and then 4 times fainter again? So when I wrote that stuff up, and I sent it to Astrophysical Journal, the editor at the time was Chandra Sekhar, and he sent it to rivalries, peer reviewing. And one of the peer reviews says this is utter nonsense because we know that X-ray sources don't vary. And then Bruno was so kind to call Chandra. And Bruno says, I know Walter Lewin. I've looked at the data with him. You better publish. And they did.
That was exciting.
Yeah, I think for me that was the first time that I felt I had really established myself as making a real dent in X-ray astronomy. I gave a talk here at MIT about that. And the 2 giants in X-ray astronomy of the world, Riccardo Giacconi and Herb Gursky, from across the street where ASNE was in Cambridge, they both came to my lectures. I think they both were skeptical at the time.
How old were you then?
Well, I was 67, so I was 31 years old, right? Yeah.
So a little later, in 1976, your research into X-ray bursts put you at odds with other scientists, most notably Josh Grindlay at Harvard. You refer to this period of time as burst fever. Please explain.
In 1975, there were 2 independent groups in the world, one in Los Alamos, and one was a Dutch satellite, ANS, it's called the Astronomical Netherlands Satellite, which was a collaboration between Herb Gursky at Harvard and the group in the Netherlands, Utrecht. And it was Josh Grindley's group who discovered with ANS all of a sudden an enormous outburst in X-rays. Several months before that, something very similar, more than one actually, had been seen by the people in Los Alamos, and those are called X-ray bursts. We at MIT, under the leadership of George Clark, who was the principal investigator, we launched a satellite, which was an all-MIT satellite. It was 1975. And we started seeing X-ray bursts. Our instruments were way more sensitive than the ones who discovered it. When we built SAS, we didn't know about X-ray bursts. So again, it was a stroke of luck that we just happened to have the right instruments on board to study X-ray bursts. And I don't recall how many burst sources we discovered, but I would say at least 10 or so in a time scale of about 2 years. So we took over the entire field of X-ray burst astronomy. And one of those sources produced about 1,000, 2,000 bursts per day, whereas most others more like 1 or 2 bursts per 2 or 3 hours. And so not only did we make these discoveries with the instrumentation, but we were even able to explain, to understand the very fundamental difference between these different 2 bursts.
And there were skeptics initially, weren't there?
There were always skeptics. And of course the skeptics were at Harvard because they thought they knew, but they didn't. They just dug their heels in. They thought they were made by supermassive black holes, which is totally utter nonsense. We had almost from day one evidence that they were produced by neutron stars. But yeah, there were skeptics. But you can't listen to skeptics. None of my papers were ever reviewed, believe me. I must have published close to 100 papers on X-ray bursts.
So during your career, how common were rivalries between researchers? And how did your rather intense temperament factor into those situations?
Well, rivalry is the necessary consequence of the American system. We have to write proposals. And these proposals are peer-reviewed. You want to make observations, say, with balloons, you need money for those balloons. You need money for the helium, you need money for the telescope. Later, when the satellites came along, you want to make observations. You have to hire postdocs, you need computers, you need money. We at MIT at that time, as faculty members, didn't even have summer salary. You had to come up with your own summer salary for 3 months or 2 months. So you have to win a proposal. You have to write a proposal that is better than the competition. And you know who the competition is, believe me. So that means rivalry, right there. Now, as far as the temperament is concerned, with the one exception, and I may be biased because I see it, of course, through my eyes, with the one exception, which is that the situation with the X-ray burst, whereby when it was blatantly clear to anyone in the world that these X-ray bursts were the result of thermonuclear reactions on the surface of neutron stars, there was still this person at Harvard, this Josh Grindley, who kept telling the world that they were not. He even published, when it was already completely clear, a ridiculous paper, a theoretical paper, to prove that they were produced by massive black holes, 100, 200, 300 mass black holes. A neutron star is only 1.5 the mass of the sun. And so that caused at times at meetings and even at social meetings sometimes some emotional friction.
I'd like you to talk a little bit about your collaboration with Jan van Paradijs.
Jan van Paradijs got his PhD in Amsterdam in the Netherlands. And the boss there, the director of that institute, was Ed van den Heuvel. And Ed van den Heuvel wrote one day a letter to George Clark. We have here this young Jan van Paradijs, this young astronomer. It looks quite bright to us. Would it be possible maybe that he works 1 year at MIT? So George says, well, you are going to give a talk in the Netherlands in a few weeks. Meet with Jan. What do you think of him? That was shortly after I discovered the rapid burster, this source which has 1,000 bursts per day, by the way. So he was in my audience, Jan, and we had dinner that evening. And what I realized was that I am a physicist, but he is a real astronomer. I'm exaggerating a little bit now, but I don't know what an A1 and an A2 or a B3 or a G4 star is. That, for him, was pea soup. That's the way he was brought up. So he was a beautiful complement to our group. He could really bring in the astronomy. He could say, perhaps we should do some optical telescopes or whatever. Mm-hmm. And so I recommended to George, yeah, we should hire him. So Jan came in my life in 1979, maybe it was 1978. We became the closest friends that you can ever imagine. We've published 150 papers together. We were more than brothers. We lied for each other. We laughed together. We cried together. But he died. He died young. He was 10 years younger than I was. He died in 1999. So how old was I in 1999? I was 66, so he was 56. He died of cancer. It was a terrible, terrible way he ended his life.
And did the collaboration take place at MIT over all
It
those
started
years?
1 year at MIT, and then I went every year to Amsterdam. Every other year he came to MIT. Then I had an Alexander von Humboldt Award in Germany, and that was close to Amsterdam, so half the time I was in Amsterdam and half the time he came to Germany. I have only one picture in my office. I don't have any pictures of my children, not of my parents, not even at home, except for paintings. There's one picture in my office. It's a picture of Jan.
You had a wonderful friendship, collaboration with him.
It was more than that. When he died, part of me died.
In 1997, you received a NASA Group Achievement Award for being part of a team that discovered, on December 2nd, 1995, a bursting pulsar near the center of the Milky Way galaxy. Can you describe that day, that moment of discovery, the setting, how it happened, how it felt?
Rather insignificant. The great discovery was when I was here at SAS3 working day and night and saw the data coming in. This data was obtained by the GRO, the Compton Gamma Ray Observatory. I hope I have the name right. And Jan, at that time, was married with his fourth wife, Chrissa Cuvilioto, who worked in Huntsville, Alabama. And one of the experiments on the GRO, on that spacecraft, was run by the group in Huntsville. And so Jan got involved. Mm-hmm. And since Jan and I exchanged graduate students, sometimes my graduate students worked with Jan in Amsterdam, sometimes his worked with me, Chrissa, Jan and I worked out a collaboration which was led by my graduate student Jeffrey Commerce. And there was an agreement that whatever came out of that particular set of data would be jointly owned by us and would be published jointly by us. You often make those agreements ahead of time to avoid misunderstandings, bad feelings, if all of a sudden there is a brilliant discovery and then someone says it's really mine. And so one day, when neither Jan was in Huntsville, nor Chrissa was in Huntsville, nor I was in Huntsville, nor Jeffrey Commerce was in Huntsville, it was the group leader there, I should remember his name, but I don't, who actually saw in the data burst coming out. Mm-hmm. But it was also a known pulsar. A pulsar is an object that produces X-ray blips every so often, mm-hmm. 3 seconds, 6 seconds, or 100 seconds. And up to that moment in time, the combination between a pulsar, X-rays going like this, and bursts had not been seen before. Mm-hmm. So in that sense, it was like a bombshell. So here is a pulsar that is bursting. And so we were informed by that. There was an International Astronomical Union circular, and our names were on it. Mm-hmm. My name was on it. Mm-hmm. I don't even think, I'm not even sure whether Chrissa Cuvilioto was one on it. It may have been the group leader there. And then when we finally published it, all our names were on it. Mm-hmm. So there was never the emotional impact that the discovery of the rapid burster had when you're standing in SAS3 on the 4th floor of Building 37, and out of the data comes this crazy thing. There's never anything like that. You know, we were told on the phone, by email. And it was an important result. And you must understand that these NASA awards, in a way, are quite arbitrary. Mm-hmm. There is no doubt in my mind, and everyone would agree with me what I say here. It is not has nothing to do with arrogance. What I really deserved for was a NASA award for my work on X-ray boosters,
Okay.
and I never got one.
Okay. Yep.
For reasons who knows. And here was all of a sudden GRO, and NASA needs publicity, another major discovery made with GRO, and so awards, article in the newspapers, etc. And so I don't even mean you get a diploma. You know what I did with the diploma? In the trash can. It meant nothing to me. I'm happy that I was part of that group, and it was certainly an important discovery, no question.
But the most
But
important,
it was not something that emotionally,
Yes.
for me, was anywhere nearly as important, nowhere nearly as important as the golden days of X-ray bursts. Nowhere nearly.
I'd like to shift gears again and go back to talking about your passion for teaching, for which you've won numerous awards. What makes you such an effective teacher, and how would you describe your philosophy around teaching physics?
I think I am an effective teacher for a variety of reasons. I often get questions daily by physics professors from all over the world, literally from all over the world, to ask me the same question. And then I say, have you ever looked at my lectures? Can't you see how different they are from yours? Can you not at least mention 10 things that are different? Not just one thing, but 10 things that are different. It is your passion. It is your imagination. It is your commitment. When you think of a lecture, I think of it like the way an architect building a house. Mm-hmm. I think of my lectures truly as works of art. You build them slowly, and they become one unity. You cannot just shave off a little piece or add a little color somewhere. And that takes weeks thinking, walking on the beach and thinking, how am I going to structure this? And I almost always do it in a different way than books do it. It's dry and boring. Mm-hmm. I derive every equation that I think is important to be derived with a piece of chalk on the blackboard. If you show a derivation on PowerPoint, that's criminal. That's a crime. I've never committed that crime because the students can't follow it. So as I work it out on the blackboard, I slowly make them aware of every single step. If I want them to copy that in their lecture notes, at least I have to have the decency to also write it, because otherwise you might as well say it's in the book. Then I try to once we have the derivations and once we have what people call the dull equations, which people in high school are scared about, right? Why do people do so poorly on physics? Because they see equations and have no idea what they mean. And then when they get an exam, they shove some numbers in there and they hope that the right number comes out. I make them see through those equations. I make these equations part of their world. I try to connect them to their world wherever possible. And I do that by giving examples which, if possible at all, are not the standard examples. And I do demonstrations which, if possible at all, are not the standard demonstrations. Demonstrations that they will never forget in their lives. And so then my enthusiasm radiates away from me. And all this preparation that goes into it, which is phenomenal. Mm-hmm. I dry run a lecture. I first build a house. Then I dry run it 3 weeks before I give the lecture. It's always too long. I have to cut a little back. Mm-hmm. Empty classroom. A week before the lecture, I dry run it again. At 5 o'clock in the morning. of the day of the lecture. I am alone in the lecture hall with no one, and I dry run that lecture again. It becomes a performance. It becomes a work of art. Is it conceivable that I make a mistake on the blackboard? No, because it's a performance. You've done it so many times. And it is all that together that makes it a piece of art.
How many hours do you prepare for each lecture?
It's hard, you know, because it begins really walking on the beach. But I would say roughly 50 hours. That's a reasonable number. If I gave the same lectures that I have given before again, it would still be 50 hours.
Okay. So the lectures that we captured in 1999, are they the result of a 20-year process where you modified and improved over those years?
Not as much as you think. Okay. People ask me that question often. No. I don't think that my 1984-802 lectures, which was the first time I lectured 802, was any different from my 2002 lecture, which was filmed. Not very different. The same Walter Lewin, the same style.
Okay.
What is very important is a sense of humor. Right. You have to make them laugh. Right. You have to challenge them. Right. I can make my students cry. I can make them stop breathing. Larry, if I want to, I can make them wet their pants.
The tapings that we did together are benefit from 20 years of preparation, 20 years of honing your craft. And I also sometimes think that we captured you at the top of your game. Is that accurate?
Tell us what again?
That we captured you at the top of your game.
I could not improve on that, if that's what you mean. Larry, something that strikes me almost every day. I get questions, typically 24 questions per day by email, fan mail I call that. And then people ask me physics questions, right? And then they ask me specific questions about a lecture. I always say, which lecture, 801, 802, or 803, what is the number of the lecture, how many minutes into the lecture? So they tell me that. And then I start 5 or 10 minutes early. Without exception, I say to myself, what a brilliant lecture. I can never do this again. How could I ever improve on that? That is fun. The way I built that up so carefully and in such a way that it climaxes always. In other words, it starts in a way that students say, hey, why would he start that way? They wouldn't have no idea. And by the end of the lecture, they say, now I understand why he started that way. That's the architecture of the house. Truly, it is sometimes amazing. Even my talks for kids. I recently watched again a lecture for the wonders of electricity and magnetism. Thank God this is on tape. If ever I had to give that lecture again, I could never do any better. Right. At best, I can duplicate myself.
Right. Well, it is a wonderful, wonderful body of work. I wanted to ask more about teaching and how it relates to the research that you did. Have you had moments of teaching, whether in front of a lecture hall or tutoring a student in your office, where you experienced the same kind of exhilaration or accomplishment that you felt when you discovered that X-ray burst?
Not during lectures, but during the 10 years of unbelievable email messages. What I receive every day in the mail, how I have changed the lives of people you cannot even imagine. This morning, again, Professor Lewin, I was retired. I didn't know what to do with my life. I felt bored. I was depressed. I discovered your lectures. I came to life again. Professor Lewin, you've changed my life. I now look at the sky again. And I know why the sky is blue. And I love it. And I ask myself questions that I have never asked before. My lectures Larry, is a new way of seeing. That's really my goal. I make them love physics. And that's a new way of seeing. It is very naive to think, if you lecture Maxwell's equations, totally naive to think of any professor here at MIT that a month after that they remember Maxwell's equations. Forget it. Maybe the night before the exam, and then it's gone. But the Maxwell's equations have a beauty in them that I make them see that beauty. I spend a whole lecture on that beauty, and then I tell them that this is a highlight in their life, because this is the first time in their life that they see a complete field theory and understand it. And I hand out flowers to every single student, to 600 students. I buy 600 daffodils, and every student comes and gets a flower. Now, 30 years later, they remember the daffodils. A month later, they don't remember Maxwell's equations. And so, is that important? It is not important that they don't remember Maxwell's equations. But what is important, that because of the way that I connect it with this momentous day and with handing out the flowers, it becomes a new way for them of seeing. And that's what I try to do wherever I can.
So your lectures are clearly a performance. And
they are a performance.
They are, and the demonstrations, I feel, are a key part of the performance. Where do the ideas for the demonstrations originate, and what are a few of your favorites?
Well, the majority of them were already present at MIT when I came here. I have added a substantial amount, and I have modified quite a few. And it is often the modification that gives it that Lewin twist, that unexpected thing, to challenge them. What is your question again? My favorite.
What are a few of your favorites?
Okay, if you think about it, that I must have done, for the 3 different courses, 801, 802, and 803, if I round off, roughly there are about 1,000 demonstrations that I do. On average, between 5 and 10 per lecture. And there are 35 lectures on 801, 35 on 802, and 30 on 803. So you can come up with roughly of the order of between 800 and 1,000. They are all wonderful, because each one tells a surprising story. And I try to give it that surprising twist. A classic, but that's not necessarily my own preference, a classic one in a parallel with the Maxwell's equations is you derive in class the period of a pendulum. A pendulum is a piece of string with an apple and it swings, right? And you derive that in class. The student sitting there, he writes on the blackboard, they copy it, and there's the equation. Okay? The length of the pendulum is in the equation with a nice letter L. The gravitational acceleration of the Earth is in the equation. Small letter G. And then you say to the class, we must have made a mistake. Professor Lewin making a mistake? Because the mass that is hanging on the pendulum is not in my equations. That must be wrong. And then they say, yeah, that's bizarre, that the mass is not in the equation, because whether you hang there 50 pounds or 5 pounds or 100 pounds at the end of the same pendulum, for sure that should make a difference in how long it takes for the pendulum to swing around. You may imagine a huge 100-pound object would probably go way slower than a 5-pound object. So I said, well, maybe it is independent of the mass. Maybe the mass doesn't enter into it. And then I bring that to a test. I take a 30-pound object and I hang that on a 5-meter long pendulum and I swing them 10 times. They get a very high accuracy because my reaction time is a tenth of a second. If I swing them 10 times, I get the period. A period is defined as one complete swing to 1/100th of a second. So we know the period to 1/100th of a second. Remember, coming back to accuracy, how important that is. And then I say, let's now see whether it depends on the mass. What do I do then? I hang on that pendulum. I hang on that pendulum. The class goes bananas. Their professor hangs on a pendulum. He times himself 10 oscillations, and within 1/100th of a second, the same result. Do you think that they will ever in their life, ever forget that the period of a pendulum is independent of mass? No. It is not because the M was missing on the blackboard, there shouldn't be a mass in the blackboard, but it is the way that the drama that I add to it, by hanging on it. And hanging on it is very difficult, because if you would sit on the bob, then the center of your body goes up, right? That means the pendulum is effectively shorter, and you would get a different period. So sitting on it is not enough. You must lie on it like this, and that's extremely painful. But that's the price you pay.
Right.
And they will never forget that. And that has become almost my logo. It's even used by iTunes U. When you turn iTunes U on, you will see Walter Lewin on the pendulum.
It's also, that's the picture that's on the cover of your book.
It's also, yeah, it's right. Yeah, it has become my logo, yeah.
Let's go
so
back
when people ask me I get lots of requests for photographs with signatures. I always send them one that I'm swinging in.
So let's go back to the makings of this internet phenomenon. You were an early adapter at MIT for
I was what?
An early adapter at MIT for using video delivery in support of teaching. In 1984, you started offering physics problem set help sessions for delivery to students via the MIT cable system. How did that come about, and how were they received?
All right, was it 84?
I believe so, yeah, give or take.
Craig just said 1990. I think 84 is more accurate. I remember there was a meeting of the physics department when someone suggested that perhaps what would be a nice idea to have maybe 1 hour per week. I think it was Professor King and it was Tony French, but I'm not even sure whether, I know it was Tony.
Well, Edwin Taylor was also involved in the early ones.
It could be.
Yes.
And so wouldn't it be nice if students could call and then ask questions? And so the whole thing was improvised. Wasn't so successful. And I think it was Tony French who came to me once and said, Walter, I have a feeling that you might be able to do it differently and maybe better. And I said, well, I'm going to give it a shot, willing to give it a shot. I would not want them to call. I would look at the homework assignment. I would give a 10-minute review. And then I would pick out the most difficult problems. Without solving them, I would give them a hint, make a drawing, a parallel, and slowly bring them to a point that I say, well, now it's in your hands. I help them. And these help sessions became so popular that upperclassmen on Friday told me they would get a crate of beer and they would be drinking beer and seniors would be watching my 801 help sessions. And that went on for year after year after year. And you were part of that. And then it was Dick Larson, who was also part of that.
That was many years later. We're going to get to that. But
It was not so many years later. It was during the help sessions that Dick said, Walter, you have a style. It is eccentric. It is so unique. This is the way you do your help sessions. When you are going to do your lectures, they got to be taped.
Right, right.
And
right.
he got funding for taping. He had that vision. It came out of the help sessions.
I understood. And that was some 15 years later, in fact, 84 to 99. But what I wanted to go, in terms of the help sessions, did you get feedback? What, for example, did student performance in those classes improve? Did you ever get any of that kind of feedback?
It's unmeasurable.
Okay.
It cannot be measured, unfortunately.
Right.
By the way, those help sessions were shown also for 6 years at the University of Washington TV.
Yes.
They had a TV station, but they had no programs. It was not a cable. It was all over Seattle, 2 million people.
Right.
And they had heard, I don't know from whom, that there was a lecture series 801 by Bob Ledoux and Walter Lewin, and they knew about the help sessions. And so they persuaded me to give them permission to use them. I said no, because I didn't think they were professional enough. They were not edited, for one thing, at least not the lectures. But they kept pushing on me, and I finally gave in. And it's interesting that Bill Gates wrote me later that that's how he got to know me. Mm-hmm. He got to know me when my lecture went on the air in 1995, every day in Seattle, Washington.
Through the University of Washington TV cable
University
system.
of Washington TV.
Yes, yes.
Yeah.
And I recall even back then that you used to get fan mail from students of all ages, including students in their 80s.
The range is about from 5 years to 95. Yeah, 5 years. I'm not joking.
Yep. So that was in 95, and those lectures were...
No, those were help sessions. 95
sessions.
were still help sessions. No, and the Bob Ledoux, Walter Lewin lectures 801.
Exactly. And those were very basic single camera recordings of your...
single camera recordings.
Yep, yes. And then it was in... '99 that Dick Larson led the effort.
3 cameras.
Yes.
One handheld camera. Handheld cameras, very important.
Yes. It was actually, was it 4 cameras, Craig? 3 cameras.
I think it was 3, yeah.
Yes. And it was rehearsal, and so what we were able to do was to capture Walter Lewin's lectures at a very high level.
But it's very interesting. And I think it's important that this goes on record. So Dick Larson somehow had the vision that the time was right for putting things, videotaping, and then maybe someday, somehow, have other universities profit from that. How, I think, was not so clear yet in 1999. Then in 2002, he got again funding for my 802. In 2001, OCW came on the air. We said, well, you can use the lectures from Walter Lewin, but they didn't have the software yet. They didn't know yet how to do the video streaming. So they said, we can't use them. 2 years later, they could. And so my 801 and my 802 were among the very first lectures, together with Strang's math, to go on the air. And I would like to think that we really made OCW in the early days. They were amazingly popular. Mm-hmm. I then realized that I should also do 803. So I went to the physics department under the leadership of Mark Kastner and under the leadership of Tom Graytek. And I said, look, 801 and 802 are amazingly successful. I would like to also have my 803 videotaped, but Dick Larson has now a different position and cannot get money anymore. I got an email. We are not interested in taping Walter Lewin's lectures. So you see, there are people at MIT who have vision, and there are some who don't have vision. I got the money anyhow for 803, not through Dick.
Mm-hmm.
So we now have 801, 802, and 803, right. 94 lectures.
Right. And then we've also been able to add to those by taping some of your one-off lectures. So, and all told, you have over
103 lectures.
103 lectures, and you've become
94 course lectures. Right. And then there are about 7 on MIT World, talks I've given for children, for kids and their parents. The Sounds of Music was very popular. The Wonders of Electricity and Magnetism. For science teachers, I have given talks, and they are on MIT World. And then I gave at Northwestern a talk about the birth and death of stars. Mm-hmm. It's the only one that was not taped at MIT. And recently I gave one in the Netherlands, which was also not taped by MIT, which is also part of it now.
So
I have 103 total.
103 total, and you've...
And then my art lecture, 2004 IAP.
Mm-hmm. Right. And you've become an internet celebrity. What surprised you most about achieving this celebrity with these online lectures?
Well, it came, of course, in a adiabatic fashion. It's not something that happened overnight. It was a slowly growing thing. I never conceived that the time would come that 2 million people would watch my lectures every year. It's almost a full-time job for me nowadays. Exaggerate a little bit, to answer all the fan mail, because everyone gets an answer. I get about 30, 40 messages each day. It was then in the year 2007, on December 19, that the New York Times wrote an article about me on the front page. And what was the colored picture on the front page? What do you think the colored picture on the front page was?
You in the pendulum.
Walter Lewin hanging on the pendulum. And so then publishers started to call me. I got 25 publishers who wanted me to write a book. Agents started to call me. And I finally decided to start writing a book and get a co-author, which is Warren Goldstein, who did very well. And that book is now being translated in 13 languages. I'm going to Barcelona next month, where the Spanish book will be released. There will be a lot of hocus pocus, television, press release, television programs, radio interviews. There will be in April a similar one in the Netherlands. The one in the United States is already out for 1 year. Mm-hmm. Russia will be coming up shortly. And the Germans is already out too.
How exciting. The Boston Globe just named your book one of the top science books of 2011.
One of the top 10, yeah.
One of the top 10. And you also gave a memorable lecture to kick off the publication of your book in 26-100.
At the end of that lecture, I cried. Mm-hmm. Because I thought it was going to be my last lecture in 26-100. It's not so sure. It's not so clear that it will be my last lecture, mm-hmm. because MITx is coming up.
Yes.
And they have approached me for MITx.
Wonderful.
In which case,
right.
I may be coming back to 26-100. Were you there in that lecture?
I was. That lecture was certainly, I think, one of the. What was so exciting about that lecture was it was the best of Walter Lewin. It was a combination of your top or most favorite, most popular demonstrations. You delivered it masterfully. We recorded it in high definition, and we had the expertise of Craig Melanese switching that lecture.
What does that mean, switching that lecture?
Directing. He directed that lecture.
He directed it.
Yes.
There were 700 people in 26-100 who were standing in the back because there were only 550 seats. It was absolutely packed.
Right. Right.
May 16, I will never forget that. May 16, 2011.
And it can still be, and it can also be seen online.
Oh yeah, it's one of
So-
my 103.
Right.
So when I said to you 103, it's one of them.
Yeah.
It's called For the Love of Physics, by the way.
So we've talked a little bit about the emails that you receive from viewers. A common theme in many of these, which you've already pointed out, is that you have changed people's lives for the better. How is it, do you think, your lectures have had that impact on people?
Say the case.
How is it that your lectures have had that impact on people?
Because I changed the way they look at the world. They look at my lectures and they say, holy smoke, is that how wonderful physics is? If only I had had a teacher like that, I would never have hated physics. The number of people that changed their careers, students, to physics, which I'm not even proud of, it's never for me in any way rewarding when the student says, oh, I was a student in EE or in Aero and Astro, and because of your lectures I changed to physics. That is not important for me. Really, honestly, that's not my goal at all. I want them to love physics, to see the beauty of their own world. And when people are retired or when they're 5 years old and they see some of that beauty, that turns them on. It changes their lives. It changes the way they look at the world.
How do you think
the famous rainbow, I told you.
Yes, exactly.
Even the rainbow lecture alone changes their lives forever.
Right.
That one lecture, whenever they see a rainbow, not only do they think of me, but there are 4 things that they will check to make sure that they are really all there. And they never even saw those 4 things, let alone that they check whether they are there.
Right.
And so every time that they see this rainbow, that knowledge is what I call the invisible beauty. It is the beauty of knowledge that adds over and above to the colors that everyone can see in this. Everyone can look at a rainbow and say, oh, how nice, it's red, it's blue. And if they turn around and you say, was blue on the outside or on the inside of the bow? They have no clue. And then you say, have you noticed that there was a huge difference in brightness of the sky inside the bow and outside the bow? They say no. Then you say, have you ever noticed that there is a second rainbow? They say no. I said, have you ever noticed if there was a second one that the color sequence is reversed? Never seen it. But from after my lecture, they will check that there is a secondary. They will make sure that red is on the outside of the primary bow. They will make sure that red is on the inside of the secondary bow. It's a disease. It's a disease. And I cannot even cure them anymore. And I don't care. It's a disease for life. And they always will notice that the sky inside the primary is way brighter than the sky outside the primary. It's a huge difference. Right. And they never saw it. They looked at it, but they never saw it.
So your lectures have given people a mechanism for seeing things in a different way.
A new way of seeing. Isn't that what I said earlier to you?
Yeah.
And therefore starting to ask questions in areas which I didn't teach, asking questions in their lives which they never would have asked. In other words, I enrich their lives by the new way of seeing. They then try to expand on that on their own, and often they write me. They often do that.
Let's shift again to talk about another one of your passions, and that's your passion for art. You're a serious student and collector of modern art. Could you tell us a bit about the origins of this passion and how it shows up in either your research or your teaching?
My parents, after the Second World War, started a very interesting art collection. They bought largely art from Dutch artists and mostly from artists in The Hague, which is the town where they lived. So I was raised in a climate whereby art was important. I would go every Saturday to an art gallery in the Netherlands. I would go so often to the museum, the General Museum, that I would even start to take my class and be a guide and explain things. I gave lectures already when I was 15 years on art. These must have been awful lectures, but I did. As a natural extension of my parents' collection, I started to collect art myself. I have about 125 works of art in my home, more than I can hang. And then when my parents died, of course, a lot of them were added. Physics is my life, but art is my love. I'm on Facebook. I get about 2,000 friend requests every year. And I only allow people to become friends if they pass an art history test. And of the 5,000 who have tried to take the test, only 50 passed. And the rest I don't accept. So they are angry because they said, you're a physicist, and we want to ask you physics questions. Well, if you're on Facebook, you can ask me physics questions. You don't have to be friends for that. And so ask me any question, I will answer it. But Facebook for me is art. At MIT, I had for at least 6 years, outside my office at MIT on the bulletin board, every day a work of art, reproduction, with a box, and they could write their own name on a piece of paper and then tell me who the artist was. And then the 3 best of the year, I gave substantial presents at the end of the year. I no longer do that because I'm retired, but now I have 3 quizzes on Facebook per week. And I only have 55 Facebook friends. And sometimes, they love it, I ask one of them, for the next week you may choose one artist, and they feel extraordinarily honored. They may choose the artist, and then together we choose the work of art. And then I post it always at 2 o'clock in the afternoon. Tomorrow at 2 o'clock I change, and then I give the solution, and then I tell them what the next quiz is, and they come in with the answers, and they send me the answers in a way that no one can see on Facebook. You can send someone a message on Facebook that others cannot read. So I have on Facebook this art quiz.
And who encouraged you to have such an active participation in Facebook?
I don't know how it started. I don't remember. It's about 3.5 years ago. I have no idea.
One of your graduate students, or
no? I don't know. I really don't remember. I draw a complete blank there.
Well, good for you for utilizing the capability of social media.
But of course, I mean, my wife Susan is has a bachelor's degree in art history. That's really the art is the glue between us. I mean, there's every major exhibition in New York, Washington, Philadelphia. We go, everyone. When the famous Willem de Koning exhibit was there, which finished a few weeks ago, we went twice even.
You've also had some very interesting artistic collaborations during your time at MIT, with first Otto Pine and then Peter Strucken?
Struiken's close enough, yeah.
Strucken. Please tell me about both of those.
Yeah, well, so I was flying balloons already in 1967, and then I walked by the Center for Advanced Visual Studies one day, where Juri Kepisch was the director. And I saw a piece of paper hanging outside there, signed by an artist, Otto Pine, who is one of the founders of the Zero movement in Germany. And I didn't even know he was at MIT, but I knew of him because I know my art history. And he was asking people who could help him with a balloon art experiment. So I said to myself, well, if I don't do it, who the hell is going to do that, right? I have the balloons at the tip of my fingers, and I would love to collaborate with Otto. And so I've collaborated with Otto many, many years. The climax of our work, for me at least, was the 1,500 feet long rainbow balloon that Otto designed for the closing ceremonies in 1972 in Munich. And I was instrumental in the design of that balloon. 5 colors, the 5 rainbow colors. Little did we know that there would be this massacre of the Jewish people, and so the ceremonies were delayed by, the closing ceremonies was delayed by 1 day. Had it not been delayed by 1 day, we would not have been able to fly our balloon because the wind was too strong. But that actually in my book is a picture of that balloon. So when Kappies was no longer the director, Otto took over the show of CAVS, the Center for Advanced Visual Studies. And so we became close friends because I worked with Otto on many projects for many years. It culminated in the one in Munich, but we collaborated, I don't know, for at least 10 years. I have several wonderful works by Otto that he gave me. And so one day he calls me in my office, was not so unusual, and he says, I have a guest here, maybe you want to meet this guest. I remember Mark de Souvero was visiting him, very famous American sculptor. And so Mark came to my office and I spent with Mark a few hours. It was an experience for me. I met Klaas Oldenburg that way in my office. No, those are giants in the field. And then one day he said, he is a Dutchman. And then we have a problem with the language. He doesn't know what begincondities. How do you translate that in English? So I told him initial conditions. And then Otto said, okay, initial conditions. So he says, maybe you want to meet with this guy. I said, well, Otto, look, most Dutchmen are boring. I have other things to do. So why would I want to meet with a Dutchman? Just because he's Dutch? He says, well, okay, Walter, I know you're busy, so it's fine, you don't have to. And I said, oh, by the way, what's his name? And he said, oh, his name is Peter Struycken. I said, my parents have 5 Struykens. Of course I want to meet him. And then I said, tell Peter that I have half hour for him. I lied. The reason why I do that after half hour I can say time is up. Peter came at 3 o'clock and left at 10 o'clock at night. Peter's impact on my life is comparable but different than Jan van Paradijs. Peter made me see art. Peter showed me why I only had looked at art, why most of the stuff that I liked was trash, had no artistic quality. He built me from scratch. We went to Chicago, we went to New York, we went to Washington. He taught me about art history. He taught me how important 1 year can make, whether a painting was made in 1915 or in 1916. That could make the discovery between a major discovery or a derivative. And that, for me, is just so wonderful. It's just like science. To discover something and be first are the pioneers. To repeat it or do something similar is to some degree plagiarism.
So you're talking about the Impressionists that came after the initial ones, is that artists that are duplicating somebody else's style? Is that what you're referring to?
No, the Impressionists were pioneers.
Yes, but you're saying that there's a big...
But there's a lot of post-Impressionism which is derivative.
Okay.
Picasso in 1907 invented Cubism. Every single artist in the entire world except Matisse started to paint cubistic. When I can evaluate ages of paintings quite well, and if anything has the flavor of Cubism, you know it's after 1907, because it didn't exist before 1907. So the real pioneer was Picasso. Now, I'm not denying the enormously important contributions that others have made after him. For instance, Mondrian, who took Cubism, he started with post-Impressionism, then he took Cubism, and then he developed his own whole new world, which is called neoplasticism. Malevich in Russia started with Cubism. Everyone started after 1907 with Cubism. That was the thing. That is what string theory was 15 years ago in physics. That was Cubism in 1907. You were no one if you didn't do Cubism. But in 1915, Malevich took off in a different direction and developed suprematism. So many wonderful forms of art and completely different movements have evolved. But 1 year can make a difference. And we know that Malevich even misdated some of his paintings, put them 1 year earlier than he really made. And it is still questionable whether he did that purposely, so that later they would say, you know, he already did that in 1914, or was it that he had not dated them, and then 5 or 6 years later for an exhibit, that the art gallery holder said, well, you really should date your paintings, and that he didn't remember, and that he put 1914 on. That is possible. We don't know that. Mm-hmm. It's unknown. But there are definitely cases whereby artists purposely predate.
So that they wouldn't be thought of as copying.
They want credit for discoveries of an. Take for example, the enormous breakthrough in art. Just I may name only one. Cubism was one. Yep. The enormous breakthrough was non-figurative art. Imagine that you go from an image that you recognize, a tree, a woman, a car, a furniture, a flower, all of a sudden to non-figurative. In other words, there is no connection with nature. Okay? That happened around 1912, 13. There are 5 people who can claim that they were among them. They didn't steal it from each other. It was in the air. It had to happen. Kandinsky made one painting in 1910 that looks non-figurative. And his wife has defended him after his death, year after year, that he really was the discoverer of non-figurative art. He wasn't. It was an accident. That it was just a study. It was not until 1914-15 that Kandinsky became really non-figurative. But it was already long before discovered by Robert Delaunay, by Picabia, even Arthur Dove, American, played an important role. It was not Kandinsky, although he is being given sometimes incorrectly credit for being the first to paint non-figurative. It's a huge step. It's almost pre-quantum mechanics and quantum mechanics. It's a whole new way of looking at the world all of a sudden. Think about the impact that quantum mechanics had on physics. A similar impact did non-figurative painting have on the world, on the art world. I'm
curious as to, I've been to the Rijksmuseum. What are your opinion of the Dutch masters?
The 17th century, well, among the greatest ever. And that's not chauvinism, believe me. That is not. Right. Absolutely, but I can evaluate other periods as well. I mean, I can go back to the Renaissance, and there's Jan van Eyck, and there is Leonardo da Vinci, and so there are great periods. What is amazing, though, there's amazing. The Netherlands is smaller than Massachusetts. Yeah. You ready for this? We had Rembrandt. We had Van Gogh, we had Mondrian, and we have Willem de Koning. Those 4 changed the way that you look at the world. If you had to mention the 15 or 20 most important artists ever, they're all 4 among them. Right. And the country is this small. But the 17th century Dutch artists, although Rembrandt is generally near the top, there is Vermeer, who is unbelievable. There is Frans Hals, which is absolutely incredible. There is Jan Steen, which is incredible. But it's true that Rembrandt is comparable to Mondrian, comparable to Willem de Koning.
We could talk another 2 hours just about art, I'm sure.
Way more. Art is my love.
I can see that. So let's talk about, starting to wrap this up, let's talk about what's next for Walter Lewin. What interesting projects do you have coming up?
Right now, I'm getting almost every week an invitation to go somewhere in the world and give a talk.
That's exciting.
Yeah, but it is of course very unpractical. Some invitations are real in the sense that they say we want you here for a week. Korea wanted me recently, and Malaysia approached me. We pay you first class travel, and you get first class hotels, and you give a few lectures. And then I found out that the government of Malaysia is strongly anti-Semitic, so I said, over my dead body. Korea is now negotiating with me. Most of those invitations are because of the lectures. People stop me on the streets. People stop me in the supermarkets. People stop me in restaurants. They recognize me. And so that is everywhere in the world. They want to see Walter Lewin. They want to see him actually give a lecture.
Are you going to do any of those?
Yeah, well, I did one in the Netherlands in October, and I may give another one again in April. I give one in Barcelona in a few weeks in connection with my book. So I can combine them often. Most of the invitations I just I decline. Don't forget, traveling to Europe, 6 hours time difference, jet lag is killing you.
Okay, let's.
So lately, I am very much involved in scheduling, trying to give not more than at least no more than once a month a lecture.
Okay. Good.
I have one in Washington lined up, one in New York, one in Barcelona, one in the Netherlands for the first already for 3 months. Then there's one coming up in Russia, probably in Korea, and by the end of the year there will be many more.
Very exciting. So wrapping this up, you've spent your career at MIT, going on 46 years. What do you value most about MIT?
MIT made it possible for Walter Lewin to become Walter Lewin. That would never have happened in the Netherlands. Never. And that's not only the research Walter Lewin, my pioneering contributions in X-ray astronomy, but in a way I call it my pioneering contributions in teaching. I know that there are hundreds and hundreds of physics professors who have told me by email that I have changed the way that physics will be taught for the next 50 or 100 years.
What kind of influence have you had on the students that you've taught in terms of that, in terms of them going off and teaching?
Well, that's what my fan mail is every day.
But I'm talking about students that you actually taught here at MIT. Students that you count, students that, you know...
You know Steve Lieb?
Yes.
Okay, he was one of my students, right?
Mm-hmm.
He says, every lecture that I prepare, you are my gold bar, you are my gold standard. Mm-hmm. And every lecture that I prepare, I say to myself, would Walter Lewin have done it that way? Mm. So surely, those who had me and who became teachers, who had me here at MIT, right, obviously, strongly influenced. In fact, Steve Lieb is quoted in my book. I don't know whether you read my book. It's in the introduction.
I have.
He was in my lectures 802 in 1984.
And tell me a little bit about your thoughts about the art program, the arts at MIT.
I've never been strongly involved in the arts program, but I think the nice thing is that I can borrow works of art and hang them in my office. And I do. I have real, very nice art in my office. Students can do the same. It's not just only for professors.
Right. But the way in which arts are represented at MIT.
I mean, the School of Arts?
Just the program itself, the importance of art and the overall MIT experience.
Well, Harvard has an art museum. MIT does not. Mm-hmm. So when you compare MIT with Harvard when it comes to art, it is apples and coconuts, of course. We have a very nice collection of sculptures on the campus. Mm-hmm. It would have been awfully nice if a school like MIT had a museum, a world-class museum like Harvard has, like BU has. Mm. But then again, we have world-class people in every field that we do. In every single field, we have world-class people,
including the arts.
Yeah, but not as far as the as the collection and the museum is, including the arts. Yes.
Yes.
Absolutely, mm-hmm. But not as far as having a museum.
I agree. Yeah.
That you can go to and say, here, this is the collection. Princeton has a collection, and most of these things are being given by alumni. So once you start it, it starts to grow on itself, you see. And people who have, if MIT had an art collection, I would certainly have given them a choice out of one of my top works that I have. I have some very nice works from American early pop art. John Wesley, I have a stunning John Wesley. I have Larry Rivers. I have Julian Schnabel. They would love them, and I would then probably donate it to MIT.
Well,
I have Clemente, Francesco Clemente. But they don't have a museum, so they won't get mine.
You may still
and
have
so
an
if they had a museum, it would start to expand on itself.
What, in your opinion, could MIT do better?
What, excuse me?
What, in your opinion, could MIT do better?
The question rarely ever takes me by surprise, but this one really does. What could MIT do better? I don't think I am in a position to give a meaningful answer. There is one thing that maybe MIT could do better, but I'm not even sure that it would be better. When someone as an assistant professor comes to MIT, he or she is being told, at least in the physics department, that it's very important that you teach well. Because once the tenure decision is going to be made, oh boy, they will look at your research, but of course they will always look also at your teaching. Bullshit. They don't. I've been on countless committees. Brilliant teachers. Excellent researchers, but not the top of the world. Out. So, would do MIT better to accept some of those exceptional teachers? Maybe, but maybe not. Because after all, what keeps MIT going, of course, is also the economy. And the real brilliant Nobel laureate quality people bring in tens of hundreds of millions of dollars per year into MIT. They rake in the overhead. And so maybe MIT cannot afford to have only a small nucleus of brilliant teachers who are not outstanding in research. Mm-hmm. So I don't feel that I am in a position here to make a value judgment.
Well, in your case, you were both a very accomplished researcher and a brilliant teacher. So it certainly...
And we have several at MIT.
Yes, we certainly do.
We have several.
Right. So looking back...
I think very highly of Donald Sadoway. Mm-hmm.
Sure.
Brilliant researcher, brilliant lecturer.
So looking back, What have been the most rewarding aspects of being a professor?
The fact that 2 million people watch me every year. And that I've changed, now more important, I have changed the lives of hundreds of thousands. So it's the 2 million per year is an ego trip. That's not important. Mm-hmm. What is important, I've changed their lives. And I see that every day, Larry.
Sure.
Every day. That is way more rewarding for me than some interesting discoveries that I have made in X-ray astronomy.
Walter, you
and as Neil Pappalardo said on his interview,
yes,
Walter Lewin's lectures will still be watched 50 years from now. And I actually believe that.
So do I. So do I.
Bill Gates has watched them all 3. He wrote me, handwritten note, 3 times. He's seen all my lectures 3 times.
So finally, Walter, you end the first chapter of your book, For the Love of Physics, with the sentence, "Physics illuminates the workings of the world in its astonishing beauty and elegance." Offer us a couple of examples. Offer us a couple of examples of where that takes place.
The beauty of the world?
Where physics illuminates the workings of the world in its astonishing beauty and elegance.
Well, you want to use the word rainbow, by the way? It's full of physics. Physics is not even so simple. Isn't that beautiful? Walk outside and look at the sky. It's blue. It's physics. Why is the sky blue? Look at outside. Why are clouds white? That's all physics. It's all around you. Musical instrument. There you go. You're helping me. It's all physics. I give a lecture on when we talk about resonance. I let students come in with their musical instruments. I let them play. I make them see the difference using oscilloscopes between what a violin is and a cello. It's everywhere around you.
Well, thank you, Walter, for helping all of us see the world in a different way.
Larry, I have been privileged and honored that I've been able to teach at MIT for 43 years. And this interview was a pleasure for me too.